Hello, college algebra students. This is section 4.3, a video to replace lectures from last week that were massively interrupted by bad transmission on Cisco WebEx. You, I assume, are used to exponential functions, and they're nice graphs here with these horizontal asymptotes, y equal to 0, every single one of them. Every single one of them has a y-intercept, 0, 1, whether it's the base is 2, e, 3, or 10. Remember, e is about 2.7, so it's in between these two. You're used to these graphs and the fact that because they pass the horizontal line test, their functions must be invertible, or one-to-one. Notice also that their domains are all reals and the ranges are all positive reals, no zero, no negative. So to find their inverse relations, which are going to be functions, because the original passed the horizontal line test, the reflection of these graphs across y equal to x gives you functions. Here they are for each one. If you reflect that across y equal to x, you get this one, and so on and so forth. So for each of these functions I had up here of base 2, e, 3, and 10, here are their logs, base 2, e, 3, and 10. Remember that log base 10 just gets called the log. This is just the log of x, and that the log base e gets called the ln for the natural log. Okay, so apart from those nicknames, there's nothing new here. The inverse relations of these functions are actually functions. They pass a vertical line test, and now they all have a vertical asymptote, x equal to 0. Notice how that is telling you that the domains of these functions are, well, whatever the range was of the original functions, that becomes the domain of the inverse functions. So the range of the exponential functions was from 0 to plus infinity. Therefore, the domain of these log functions are from 0 to plus infinity. So no negative inputs, no negative inputs, no negative inputs, and no zero inputs. However, that does not mean that the outputs are not negative. In fact, the range of the inverse function has to be the domain of the original, right? And we had sold you on the idea that exponential functions are defined for all reals. So now you have to buy it that the range for all logarithmic functions is all reals. So you can see there can be negative outputs from a logarithmic function. In fact, many of them, but not negative inputs or zero inputs. Notice that 1, 0, 1, 0, 1, 0, 1, 0 is the x-intercept for all these, just because the y-intercept for all those was 0, 1. So yes, you can have a zero output, negative output from the log function, just not zero input, not negative input. So if you are confronted with having to graph the log base, say 4 of x, or in fact what you really need to do is graph a graphing transform of the log base 4 of x, remember what that word base here means. The log base 4 of x is the inverse function. Every logarithm is the inverse function of an exponential function where 4 is its base. So to graph this function and continue to looking at its graphing transforms, you really should graph y equal to 4 to the x first. You know all kinds of things about y equal to 4 to the x. Human brains don't mind working with exponential functions nearly as much as they do logarithmic functions. So if you graph a few points on y equal to 4 to the x, and then put down the line y equals x and just reflect across that line y equal to x, you'll get the perfect graph of log base 4 of x. Take, for each of those points, just flip the x and y coordinates, which is what actually reflecting points across y equal to x actually does. So 1, 4 reflected over here becomes 4, 1, 0, 1, the y-intercept of 4 to the x, becomes the x-intercept of the log base 4 of x. Negative 1/4 over here gives you a value over here of 1/4 comma negative 1. More importantly, though, this horizontal asymptote, y equal to 0, that every exponential function has, becomes the vertical asymptote that every logarithmic function has. So y equal to 0, switch out the y for an x, becomes x equal to 0, vertical asymptote, and now you understand the graph of the log base 4 easily. So when you're trying to deal with the graphs of logs of some base, graph the function, the exponential function from which it inherited all its properties. So now it's easy for you because you know that the domain of 4 to the x is all reals. And therefore, that's going to tell you the range of the log base 4 of x is also all reals. Looking back at the green curve, its range is from 0 to plus infinity, because you can't get an exponential to have an output that is a 0 or a negative, right? No exponent on 4 is going to do that. So the range of 4 to the x is from 0 to plus infinity. Well, that tells you what the domain of the log base 4 has to be, from 0 to plus infinity. And if you've been drawing the graph correctly with the vertical asymptote here and reflecting that curve, that also tells you the domain is from 0 to plus infinity. So continuing, same thing, of course, applies for the ln of x, which if you just remember, that's log base e of x, and you remember that e is about 2.718. You can easily graph that without all the other graphs, like we did on the first page here. E to the x is invertible. Its inverse is this function log base e, or ln of e. So all kinds of things about logarithmic functions come easily if you just remember what the base is. The log base e is what is meant by the ln of x. That's just something you have to memorize. That's the only time that it's not explicit. The log of x, when they're not being explicit, really means the log base 10 of x. So e to the x is the inverse of this function, and 10 to the x is the inverse of that function. Most students find those easy to draw. Now, your book just defines what a logarithm is. It says the log base b of some x is going to be equal to y if and only if b to the y is equal to x. Well, that's all very nice and good, but kind of hard for students to get from this expression to that one. So when a colleague of mine about 20 years ago pointed out this little trick, I've been using it ever since because it seems to really help my students. So if you have log base b of x equal to some quantity, that's an equation, a logarithmic equation. You can write the equivalent exponential equation really quickly by drawing this kidney bean shape around the base b, which is lower, and this y value, which is higher up. That reminds you, oh, it's b to the y. You just write that. And then anything that's not inside the kidney bean, you just put on the other side of the equation. So for example, you're asked to figure out what's the log base 10 of 10,000. Okay, so using the kidney bean trick, it's easy to see that we should be writing 10 to the y is equal to 10,000. Okay, now over here in exponential land, that's really easy for us to figure out because everybody knows that 10 to some number of zeros is the same thing as 10 to that number of zeros. So 4 zeros here. Oh, that's just 10 to the 4. So 10 to the y is only going to equal 10 to the 4 if y is equal to 4. And so then you come back over here and you say, oh, that's what log base 10 of 10,000 is. Log base 10 of 10,000, 10 to the 4, of course, is just equal to 4. Of course, everybody remembers what a logarithm does. It asks you, what exponent should I put on this base to make this number? Yeah, it's a lot more easy in hindsight. For example, what's the log base 2 of 1 over 64? We don't know what it is. Let's just throw down a variable y, call it that. As long as I have just a plain log over here, nothing else written over there, I throw on the kidney bean. That makes it easy for me to write the equivalent exponential equation. 2 to the y is equal to 1 over 64. Now 64, we all know, is 2 to the, let's see, 2 to the 6th is equal to 64, right? Because 2 to the 5th is 32. So 1 over 64 is the same thing as 1 over 2 to the 6th, or which is the same thing as 2 to the negative 6, right? So 2 to the y is equal to 2 to the negative 6. Oh, y's got to be equal to negative 6. Therefore, the log base 2 of 1 over 64 must be equal to negative 6. A lot easier to solve it over here in exponential land. So when your book wants from a given logarithmic equation an equivalent exponential equation, remember the kidney bean trick. Or when the book is just asking you to evaluate some logarithmic expressions that you don't know, the kidney bean trick can make it a lot easier. You know, evaluate the log base 5 of 625. Well, we don't know what it is. We call it some variable like y. Put the kidney bean on there. Come over here. 5 to the y is equal to 625. 5 to the first is 5. 5 to the second is 25. 5 cubed is 125. Multiply that by one more. Oh, yeah, that's 5 to the 4. So, okay, over here, 5 to the y is now equal to 5 to the 4. Right. Y has to be equal to 4. Come back over here. That's what the log base 5 of 625 is. And yeah, you can check with the kidney bean trick right here. 5 to the 4 is equal to 625. Yeah. Even when the bases are fractions. In fact, especially when the bases are fractions, students get like, I have no idea what's going on here. Well, as long as you don't know what this expression is, log base 1/2 of 8. So you just call it some variable y, use the kidney bean, come over here, and look what you've got. Exponential equation is 1/2 raised to the y is equal to 8. Now 1/2 is the same thing as 2 to the negative 1. And it's being raised to a power of y. Remember your properties of exponents. A power raised to a power means multiply the exponents. Negative 1 times y gives you negative y. So on the left-hand side, we have 2 to the negative y. 8, you should realize, is 2 to the 3rd. So these two exponential expressions with the same base can only be equal if their exponents are equal. So therefore, negative y must be equal to 3. And that tells you that y, if you multiply both sides by negative 1, must be equal to negative 3. So now you can come back and say, yes, of course, log base 1/2 of 8 is equal to negative 3. And go ahead and check it by using the kidney bean trick on that. Yes, 1/2 raised to the negative 3. You can play with the properties of exponents. Will give you an 8. How about this one? Sometimes they'll ask you to evaluate something like 5 minus log base 5 of the square root of 1/5. And just give you that expression. Okay. Might have no idea what that is. Okay. Well, to be able to pull off the kidney bean trick, we got to get rid of this other term. So we're going to subtract 5 from both sides. That's going to give us, so we said we don't know what this thing is that we're supposed to be evaluating. We call it y. But we need to get a naked log over here on the left-hand side to be able to use the kidney bean trick. So I have to subtract 5 from both sides. So the opposite of the log base 5 of this terror is equal to y minus 5. Fine. And now I have a negative in front there, so I got to multiply both sides by a negative. So now I have log base 5 of the square root of 1/5 is equal to the opposite of y minus 5, which, by the way, is 5 minus y. So continuing, I have log base 5, finally a naked log, nothing out here in front of it. Log base 5 of this mess is equal to 5 minus y. Do the kidney bean, get the exponential expression that's equivalent. 5 raised to the 5 minus y is equal to, square root of 1/5. Let's continue with that. 5 to the 5 minus y is equal to the square root of 1/5. Well, remember, square roots, in fact, nth roots, roots of any degree, are really exponents. So the square root of ishkabibble is ishkabibble to the 1/2. The nth root of something is something raised to the 1 over n power. So here, this square root can be written as an exponent, and 1/5 can, of course, be written as 5 to the negative 1. So we're using properties of exponents all over the place. So I got 5 to the negative 1, its square root, what is that? 5 to the negative 1 raised to the 1/2. That's me applying this rule over here. And so now I can say 5 to the 5 minus y is 5 raised to the negative 1/2. Those two exponential expressions by, oh, your book is very formal, page 429 in section 4.3, by the equivalence property of exponential expressions. These two exponential expressions can only be equal when they have the same base if their exponents are equal. So 5 minus y is equal to negative 1/2. Solve for y. Nice little linear equation here. So we're going to add y to that side, add a 1/2 to the other side. We end up getting y is equal to 5.5. In summary, what is this expression you were to evaluate? 5 minus the log base 5 of the square root of 1/5. We called it y. We came over to exponential land, exploited all those properties of exponents, and now we know it's 5.5. That's about as nasty as those get. Let's look at problems out of the book. Section 4.3, problem number 60 is like number 59, but I'll do the even problems so that you have even more information than, remember, all your odd problems have answers in the back of the book. So we are to simplify 4 raised to the log base 4 of a minus c. Well, now remember, 4 to the and log base 4 are inverse functions of each other. In fact, if we say 4 to the x is f and log base 4 is g, then we can say the f and g here are inverses. And remember what that means. If you compose f with g on anything, you're going to get back the thing. Or if you take two functions g and f that are inverses and compose them in the other order and or operate on anything, you're going to get back that thing. So, for example, 4 raised to the log base 4 of 1,117 divided by pi, it doesn't matter what nonsense they put here, we're just going to parrot it right back here. Or what is log base 4 of 4 raised to the negative 27 over 4? Even if it has something to do with 4, we don't care. We recognize these two functions are inverses and just parrot back. Whatever was in there, we put here. So what is 4 to the log base 4 of a minus c? Just a minus c. Simplify the log base square root of 5 of 1. You might be asked to do, as in problem number 63, section 4.3 on page 439. Well, the log base square root of 5 of 1, we don't know what it is. Let's call it some variable. Apply the kidney bean trick. Now we're looking at an exponential equation. The square root of 5 raised to the y, it's got to be equal to 1. Oh, that's right. Anything raised to the 0 is 1. So y is equal to 0. Come back over here. Replace that y with a 0. Oh yeah, the log base square root of 5 of 1 has to be 0 because square root of 5, anything raised to 0 power is going to give you 1. And that's what I'm saying right here. It doesn't matter what they put. If you see a 1 there and some ishkabibble here, log base ishkabibble of 1 is equal to something. That's equivalent to saying that ishkabibble raised to the y has got to be equal to 1. Oh, that tells you why. That exponent's got to be 0. That ishkabibble could be 1776 over 3. You raise it to the 0, you have 1. Just remember 0 to the 0 is undefined. But otherwise, any base raised to the 0 power is equal to 1.